In 2022, a newly opened performing arts center faced a serious crisis shortly after its grand opening. Despite an investment of tens of millions of dollars, audiences in the rear sections of the hall heard muddled, indistinct sound, and performers on stage struggled to hear one another clearly. Two separate acoustic remediation projects followed, each adding millions more to the budget. The root cause? Sound had never been validated during the design phase. This is not an isolated story. Across the world, from concert halls in Europe to cultural centers in Asia, performing venues have faced similar post-completion acoustic failures. Each one an expensive lesson in the limits of conventional design. So where does that leave us today? A. I can now listen to a building before it is ever constructed. Working directly from architectural drawings, it calculates how long reverberation will linger, which seats will experience frequency dropout, and how changing a single wall material ripples across the entire acoustic field, running thousands of simulations in the time it once took to sketch a single plan. Today, we go deep inside the era where AI designs sound. Architectural acoustics is a discipline with more than a century of history. But, to be candid, the majority of acoustic design work has long relied on experience and intuition. Specialized acoustic consultants would study comparable past projects, work through calculations by hand, and build physical scale models to verify their assumptions. Three fundamental problems persisted throughout this approach. First, the process was far too slow. A single traditional acoustic simulation for one space could take weeks or even months to complete. Second, the workflow was brittle under change. Every time a material was swapped or a spatial geometry revised, the entire calculation had to begin from scratch. Third, the expertise barrier was prohibitively high. Without a dedicated acoustic specialist embedded in the team, architects had no reliable framework for making sound-based design decisions. These three limitations defined the state of architectural acoustics before AI entered the picture. Industry estimates suggest that approximately 2/3 of acoustic design errors are discovered only after construction is complete, at a point where corrections are exponentially more expensive than they would have been at the design stage. So how does AI acoustic simulation actually function? The core innovation is the fusion of physics-based acoustic modeling with machine learning. Traditional ray tracing methods tracked sound as it propagated through a space using millions of virtual rays, each modeling how sound reflects and scatters off surfaces. Even with high-performance computing hardware, a single simulation could consume hours of processing time. AI changes this equation fundamentally. After training on tens of thousands of spatial datasets, an AI model can accept a new space's geometry and material specifications as inputs and return reverberation time, sound pressure distribution, and speech clarity scores within minutes, sometimes seconds. In concrete acoustic terms, RT60, the time it takes for sound to decay by 60 decibels after a source stops, is predicted almost instantly. SPL maps showing how sound pressures distributed across every point in the room are generated in real time. The Speech Transmission Index, or STI, which quantifies how clearly spoken words are intelligible to a listener, updates continuously as the design evolves. Change a ceiling panel material, the updated simulation is ready immediately. This real-time responsiveness is the genuine game changer. Acoustic performance becomes a live variable in the design process rather than a final stage verdict. Enough theory for practitioners. The most important question is what an AI acoustic workflow actually looks like on a live project. The most mature and repeatable workflows currently in use break down into 4 clearly defined stages. Let's walk through each one. Step 1. BIM model integration. Your existing Revit or ArchiCAD model connects directly to the AI acoustic engine. There is no need to rebuild or re-export the geometry. The design data already in your BIM environment becomes the acoustic model's foundation. This mirrors the broader trajectory of AI-assisted BIM review, where automated systems are already reporting accuracy rates exceeding 90% for detecting dimensional errors and design conflicts. Step 2. Material acoustic database mapping. AI platforms carry built-in libraries containing the absorption coefficients for thousands of architectural materials. Select a finish from your specification, and its acoustic properties are reflected in the simulation automatically. Update the material, and the acoustic result updates with it. Step 3. Scenario optimization. The AI systematically explores hundreds of combinations of material choices and spatial variables, converging on the configuration that best meets your target acoustic performance criteria, whether a specific RT60 range, a minimum STI score, or a maximum noise level threshold. Step 4. Auralization. The completed simulation is converted into binaural audio. Clients can listen to the finished space through headphones, experiencing the sound of a building that does not yet exist. Where does AI acoustic design deliver the most transformative results? Let's examine 3 representative space types and the distinct acoustic demands each one places on a design team. Concert halls represent the most acoustically demanding environment in the built world. Classical music performance targets an RT60 reverberation time of roughly 1.8 to 2.2 seconds. This window is narrow enough that even small adjustments to material choice or ceiling geometry can push the result out of the acceptable range. AI simultaneously models ceiling curvature, balcony rake angles, and seat absorption rates to hit this target with a precision that was simply not achievable through manual iteration. A recent performing arts project in Europe used AI-assisted acoustic optimization and compressed the acoustic tuning phase from 6 months to under 3 weeks, a timeline reduction that fundamentally changes what is feasible within a standard project schedule. Open-plan offices demand an entirely different acoustic strategy. Rather than richness, the goal is speech privacy and cognitive focus, requiring RT60 values below 0.4 seconds and carefully engineered masking effects across specific frequency bands. AI simultaneously optimizes partition placement and ceiling material combinations to achieve this balance. Healthcare facilities present a third distinct challenge. Patient rooms must block sleep-disrupting noise intrusion while maintaining speech clarity for clinical staff communication, 2 requirements that sit in direct tension with each other. AI is increasingly being deployed to resolve these competing demands on a room-by-room basis, treating each space as an independent acoustic problem within a larger whole. Theory is behind us. For practitioners, what matters now is which tools are available and deployable on real projects today. Here is a grounded overview of the leading platforms currently in professional use. First, Odeon. Developed in Denmark and one of the most established acoustic simulation platforms in the world, Odeon has added AI-powered prediction modules to its mature physics engine. Its BIM integration is robust, and it remains the reference tool for acoustic consultants working on concert halls, opera houses, and large auditoriums internationally. Second, Treble Technologies. This cloud-native acoustic simulation platform combines physics-based wave simulation, specifically finite element methods, with machine learning acceleration. Treble is designed for teams that need to evaluate many design scenarios quickly, with results delivered in the cloud rather than requiring local high-performance hardware. It represents the new generation of AI-first acoustic tools. Third, spatial audio and VR auralization platforms. A growing category of tools converts acoustic simulation outputs into immersive binaural audio experiences. Design teams can walk through a virtual space wearing a VR headset and hear how the room sounds, transforming acoustic review from a spreadsheet exercise into an experiential client presentation. Fourth, Autodesk Insight's acoustic module. For teams already working within the Revit ecosystem, Insight offers an integrated acoustic analysis path with minimal additional learning investment. Acoustic performance becomes part of the existing BIM workflow rather than a separate, siloed process. We have now traced how AI is reshaping the foundational practice of architectural acoustic design. To bring it all together, AI acoustic simulation is no longer the exclusive territory of large specialist consulting firms. The tools and workflows exist today for design teams to evaluate and optimize acoustic performance directly, beginning from the earliest conceptual stages of a project, not as a final validation step. What once demanded months of specialized analysis can now be completed in hours. Clients can experience the sound of a space before a single structural element is in place. The projection within the industry is clear, within roughly 3 years. AI acoustic tools are expected to become standard components of professional design practice worldwide, integrated into BIM platforms and available to firms of every scale. Yet one important question persists. Does the acoustically optimal solution that AI proposes always constitute a meaningful or moving listening experience? Does a mathematically precise RT60 value guarantee the emotional resonance that a space will hold for the people who inhabit it? As AI becomes embedded in the design process worldwide, the tension between data-driven precision and human artistic intent is becoming one of the defining questions of our field. Where do you place your trust, in the sound that AI optimizes, or in the sound that an architect imagines? Share your perspective in the comments below.